Okay, yes, as Tina mentioned, use the chat to ask questions, and I will stop at a number of places, and we can go through what there what there is. Uh, okay, so this presentation, what do you mean by cache friendly? This presentation, you can say that it started a couple of years ago, or many years ago, depending on your context. Um, I work for Net Insight in Stockholm. We make networking equipment, and a couple of years ago, we made a new media network switch with much faster CPUs, much faster FPGAs, more CPUs and more FPGAs, and we were nearing the end of this huge undertaking of developing this new switch. And I was doing some stress performance measurements, and I was really disappointed with the result. It was nowhere near what we expected. So time to try to figure out why is it slow, and it didn't take very long to find that it's one of the central CPUs that was busy. That was like the spider in the web that controls the entire network node. Uh, and that was kind of weird. And then trying to locate what in that CPU was so busy, and it turned out it was the control daemon that primarily reacts to changes in the network topology, uh, and it didn't compute for me. Why is this daemon taking 100% available CPU when it's what it does? It sends and receives messages across the network primarily. So it should obviously be limited by latency. So why this? So then start profiling this daemon, and I found that 75% of all cycles were spent in one function. The function was named schedule timer, and I was like, why is this function consuming all the CPU? So let's go into this. Here's how it's implemented. It's a really old API. It's a C API. I have C++ified it very slightly and simplified it a little bit for this presentation. But basically, this is what it looked like. So we have a timer struct with a 32-bit deadline in milliseconds. It wraps. That is not a problem. And a function pointer callback and a user pointer, as is so common in C APIs, where you can have your private data there, and a prev and a next pointer, because this is a linked list. And some of you are probably already feeling uncomfortable now. That is all right. So the schedule timer function just iterates through the list from the end and finds a place to do its insertion. And then there is a cancel function that is very important, because the vast majority of all timers are canceled. They're only there to discover when a request has not been responded to. And this is kind of slow. And this is why this presentation, what do you mean by cache friendly, is the presentation that I wish that I had attended something like 20 years ago, because the person who wrote that timer was me. So let's dive into this. I have a mental model of how a cache works, and it's extremely simplistic. The real world is a lot more complicated. But what you can see to the right is the main memory. It's big, very big, hopefully. In the middle, we have a cache. It has a few entries, and to the left we have source code. One thing you can see right away is that the cache and also the memory is oriented in large-ish chunks, or all of them are the same size. And these are the cache lines, and all the communication with the main memory are to read and to write a whole bunch of bytes that is aligned with the cache lines. So your program will never ever write a single byte to main memory. That doesn't happen. So when we start to run the program, say that we want to read from this pointer hot, we can see that the pointer hot is to address 4004 hex. 4004 is in the cache, so we just get the value and go on. And then we want to read from cold. Cold is at hex 4048. 4048 is not in the cache. So what does the CPU do? Well, the cache is of limited size. So what it has to do is to select something that is in the cache that it chooses to sacrifice. So it takes this line. From the perspective of you as a programmer, you can assume that this is more or less random. You don't have any control over it. The CPU, of course, doesn't do random selection, I think, but you have no control of what gets evicted and what doesn't. So it chooses a cache line to evict, and there it's gone. And then it finds the memory that we wanted to read, load it into the cache. This is a slow operation. Reading from main memory into cache is something usually in the order of 100 times slower than reading directly from the cache. And now that it is in the cache, we can just do the read, and everything is good. And now we may want to write to an address that it pointed to via this also cold pointer. Also called it at 4080. 4080 is not in the cache, so it must select something to evict it. Now it happened to be 4010. Now this white rectangle there is some change to that memory that has not yet been written to main memory. So the cache and the main memory, the main memory at address 4010 does look different than the cache at 4010, and it's the cache that has the right information. So the cache must write this back to memory, and then it can evict this no longer necessary data. Select the memory address to read and get it into the cache, so we can do the write. So a cache miss is something that is slow. But now when we want to write to another address that happens to be on the same cache line, it's just a hit, we're done. But now this cache line on 4080 is dirty. That is, we have made updates to it that are not yet reflected in the main memory. So sometime in the future, and we have absolutely no control over when the write will be done to memory. And that is my mental model of how the CPU cache works, and it's extremely simplistic. So, but it includes some important aspects. So to begin with, it includes that the cache is small and it is fixed size. And if you're writing generic software that can run on any hardware, that is pretty much as you can know about the cache that your software will run on. And that it consists of fixed size lines, and data access that hits the cache is very fast, and an access that misses it is very slow. What this mental model does not take care of at all is that in reality you have several levels of caches. The laptop I'm presenting this on now has a hierarchy of 3 levels. It doesn't take care of associativity. In my simple model that I showed previously, any cache line could represent any address in the main memory, but that is not the case. In reality, they are mapped so that each memory address can only be represented in a subset of the cache lines. And for some access patterns, this can be a problem, but I'm actually not going to go into that today. And also, this excludes threading, and threading can really be a difficult thing when dealing with caches, because most CPUs today, you have, like I said, you have a hierarchy, several levels of cache, and usually the level 1 cache is, you have one level 1 cache per CPU core, which means that if you have threads that run on different CPU cores, and one thread writes to something in its cache, and a thread that runs on another CPU core wants to read the same address, then the caches must update each other, otherwise you get nonsense results, and that is complicated and time consuming. So the only thing I'm actually going to say about threading and caches is that avoid sharing mutable state across threads as much as you possibly can, because it's a major performance killer. You can probably not get away with it completely, but do your best to minimize it. And the general rule from all statistics, all models are wrong, but some models are useful. And I think this model actually is useful. I have successfully performance tuned quite a lot of programs actually by just thinking along these lines. So it's a simplification, but it helps. So I don't know, are there questions before I go on with analysis of this program?
None in the chat so far.
None in the chat. Okay, good. So what I did to, I mean, it was obvious when I saw what was the problem, but I want to just show how you can spot less obvious things and some of the tools available. So what I did was I wrote a simple program that I would definitely not call this a benchmark. This is more a program that is, in a fairly simple way, exposes how this timer data structure handles or mishandles memory. So what I'm doing is just have this inner loop where I go over 20,000 revolutions, schedule timers, and every second revolution I cancel the one from the previous revolution. So when we're done, we should have 10,000 timers remaining and potentially quite scattered through memory. And then I'm just shooting the timer callbacks one by one in a simple function that checks that if the list is empty, we return false. Otherwise, shoot the callback and cancel it and return true. And then you just loop over this until it's empty, and then we start over again. So it should show something about memory accesses. So one tool that is useful is Valgrind. It's mostly well known for checking for memory problems of various kinds with memory leaks or uninitialized data and such. But one of the tools in Valgrind is Callgrind. And Callgrind it's a CPU emulator, actually, that collects data about whole call hierarchies and the number of calls and time spent. It's not CPU cycle accurate simulation by any means, but it gives a broad picture. But then you can also say, yeah, and simulate the cache, please. So it simplifies it a little bit. It flattens it to 2 levels instead of as on this machine 3. But and by default, the level 1 will have the same will look the same as the host CPU one, but the last level cache is not. But the interesting thing is that you can actually change this. So if you're writing software that targets a different CPU than the one that is on your host, you can actually say, no, this level 1 cache that you should do the measurements on now is looks like this instead. Then I'm asking it to dump instructions. Normally it doesn't do that. It keeps more high-level information about where we are. But being able to look at instructions can really help. We can see that exactly this read instruction, this read or write instruction is where we have the cache miss. And then also a branch sim, because branch predictors, it turns out, are also important. And it's a branch predictor. It doesn't reflect the branch predictor in your CPU, but it gives some information. It is extraordinarily slow. Getting a 20 times slowdown compared to running native is not even unusual. It can be much slower than that, 100 times slower. But you can get a lot of information out of it. So let's see if we can find something out from this. Wrong window. Here we are. So we looked at the linked list program. Should be familiar, this schedule timer loop cancel timer that just unlinks something from the list. And the main program that schedules timer, cancels timers, and shoots the first one. So one thing you may notice here is that I'm using 01. And the reason is that in my experience, and this may not always be true, but in my experience, it's good enough optimization to give you a view of the data access patterns, but it still maintains enough of the program structure so that you can understand the assembly. And that is, in my opinion, quite important. So let's run Valgrind then. This is going to take a long time. It usually takes about a minute to run this one. But what happens now, it emulates a CPU. It runs instruction by instruction, and for each and every one of them, it checks where are we in the call stack, where does a read or a write hit or miss the L1 cache or the last level cache, and it dumps this in information that we can then analyze. And as I mentioned, also you can say that you want a different cache than the one you have on your target CPU. So say that you're writing software for a 32-bit ARM. You can write your software so that you instead compile for a 32-bit x86 and say that, yeah, and the cache looks like this ARM cache. And I think you will probably get a reasonably accurate result on how it looks. So here we have now, we see 2.5 billion instructions, 1 billion data accesses, 700 million level 1 misses, 70% L1 misses. That is quite impressive and not in a good way. So just from there, we have some information about something that is wrong. But here comes the really great thing. There is this tool K-cache grind that visualizes the data that Valgrind's call grind tool saved for us. And this one is quite extraordinary. So this is a very busy screen now. So you can. So we can look at here at a number of different things, what we are interested in seeing, cycle estimations, whatever. But what I'm interested in is looking at the L1 misses. And we see that 99% of them are in the schedule timer function. So we can go in here in schedule timer and see what happens. It has 66% of all cache misses are in this while check, okay, and 33% is when getting the prev pointer. So another thing that is really not useful at all in this tiny program, but it can be really useful in bigger programs, is to just see the graph of calls and see where things happen, where the hotspots are. But in this case, let's look at the assembly. So we can see 66% are here when we compare what's in the EBP register to what RBX points to. Okay, and then we have 33 when we get something from RBX with an offset of 20 hex, or 32 bytes up from RBX. So, okay, so RBX must be the pointer to the timer struct, and the first element in the timer struct is the deadline. So okay, so 66% cache misses when comparing the deadline for the timer event with the deadline we want to add, and 33% cache misses when traversing to the previous entry in the list. Okay, so I have some information here. We have a timer, and if we look at it, we can see we have our deadline, 4 bytes, and it's the first one, as I mentioned, so offset 0. Then we have padding, because the callback is a pointer. It needs to be on 8 bytes alignment. The user pointer, next pointer, previous pointer. So all in all, this structure is 40 bytes. And we saw that 66% of all cache misses comes when reading this one. And how come? Well, we get to this timer struct via a pointer, and that the CPU has no way of knowing beforehand where in memory that is. So that structure is extremely likely to not be in cache. So we have to wait for the entire cache line to be read until the CPU can check this deadline compared to the desired deadline. So here's a first rule of thumb, that when you follow pointers, have data structures where you follow pointers, assume that following a pointer is a cache miss, unless you have very good information to the contrary. So just as a rule of thumb. And then we saw 33% of all cache misses are on that one. And that is not so strange, because this one is now 32 bytes up from the start of the timer struct. And on this CPU, and I think this is really a industry standard today, the cache lines are 64 bytes large, which means that wherever in memory we have a timer, there is a 50% chance that the prev pointer is on the same cache line or not. And therefore, we see this, that 66% of the cache misses are when reading the deadline, and 33% are when reading the prev. So if we just change the order of these, so that prev and next, especially prev in this case, were closer to deadline, we would probably not see a drastic reduction in the number of cache misses, but we would see a reduction. So that is the next rule of thumb. Data that is accessed together should be stored together. And with together, I mean just the bytes next to each other so that they are almost certainly in the same cache line. So if you get a cache miss on one of them, you will not get a cache miss on the other because you have already done the work. All right. So chasing pointers is expensive. So let's get rid of the pointers. I'm going to do something that is patently stupid here now. But why not? So we can change the structure so that we have a smaller timer data struct that is just, it's 32-bit deadline. It has a timer ID. I will get to that very soon, why we need that. A user pointer and a callback. So now we have 24 bytes per entry instead of 40. And we have no pointers. And we store this in a vector, so it's a linear structure. And what happens then? Well, our scheduled timer, here's where the stupidity really comes in. So we start with making space for an insertion, and then we just look at the slots in the vector one by one, and if it's later than our desired deadline, then we move it backwards. One by one, we move them backwards until we find the insertion spot, and then we do the write. So there's a lot of work there. And cancel timer, which is the reason why we need the timer ID. Since we're now moving the data around in memory, we have no handle to find to directly access the timer with to be able to cancel it. So what we do is we do a linear search in the vector of timeouts until we find this timer ID, and then we erase it. So enter another Linux tool, perf. Perf is working in a completely different way. So perf presents statistics. perfstat specifically presents statistics from a whole program run, and those statistics are using counters from the hardware and from the Linux kernel. And you then select which events you are interested in. And this is actually one of the problems with perf. There are so many events that you can inspect, and it's really hard to know which ones to use. I find that it's often interesting to take a look at cycles and instructions, because those together is sort of a proxy for how busy the CPU is, because the CPU is capable of executing several instructions per cycle, but if it's waiting a lot due to cache misses, it can instead be several cycles per instruction. So it's an indication. Although be careful with interpreting that, because it can be busy doing something that is stupid. So be careful. And then we can look at level 1 cache loads and misses. And load misses are extra interesting because of speculative execution. I will get to that in a while. But it's fast. It's amazingly fast. This perfstat that just shows whole program statistics, it's virtually no overhead at all, because it just presents the information that is already there from the hardware and in the Linux kernel. So it's I wouldn't say it's no offset, but just about no overhead, just about no overhead at all. But then we can use perf record. Perf record is working in a different way. It uses these same counters from hardware and the Linux kernel, but it statistically pulls them regularly, which means that your result it is a statistical result, but it kind of makes sense, because if you're looking at a performance hotspot, you're obviously likely to get your samples in that hotspot. It may mean that you have to do longer runs to be able to see it. But since it's running so fast anyway, so it's not really a problem. One useful thing, I think, is to ask it to store call graph information, because otherwise you're just seeing individual functions without seeing their context. But with call graph information, and you can select various ways of getting the call graph information from a debug info or whatever. The LBR only works on reasonably modern CPUs, but not super modern. And the good thing is that it works regardless of how the sources were compiled. So that is good. So, and it's also very fast. It's not as fast as just presenting whole program statistics. So there is a small overhead, a few percent, but it's normally not a problem at all. So let's demo this one. And now things get interesting, because I have learned the hard way that this video conferencing system really wreaks havoc with the performance. And now I'm logged into another machine. And let's hope that this works. So first, have a look at the cache on this CPU. We can see it's a reasonably potent machine. Especially we have a very large level 3 cache here. But the level 1 cache, there are eight CPU cores. Each CPU core has an L1 data cache of 32 kilobytes. I don't know how many of you are so young, so old that you remember when 32 kilobytes was a thing. It's so little. I bet many of you have strings that are longer. So together we have 256 kilobytes shared across these CPU cores, but this is tiny, absolutely tiny. And then we have an L2 cache in between that is interestingly shared between pairs of CPU cores. But I'm only going to look at L1 cache today, and I'm actually not going to bother with L1I is the instruction cache. So I have a cache of instructions too, but again, since this is 32 kilobytes, it says that if you have a very long loop where you do a lot of instructions, it may not fit in 32 kilobytes. That's a huge loop body, so maybe it's not really a problem, but it's worth thinking of. So if I build this one and run the stats on it, so we can see, well, one thing we can see is that it went a little bit faster than running in Valgrind, a tiny little bit faster. So 3.5 seconds instead of a minute. Approximately the same results. But if we now compare with linear array, so I have the timer data as I showed you, and this schedule timer that moves all this data around in the huge vector, so to find an insertion spot, and likewise a cancel timer that finds the thing to erase, and the loop. Let's see. What this can do then. So 3.5 seconds for the linked list. And 6.9 seconds for the linear array. And what we can see is that there are a lot of instructions, but also a lot of instructions per cycle. A lot of loads, actually more loads than twice as many loads as in the linked list. But since partially it's because the number of misses are lower. But also, since the CPU has something that is called a prefetcher, that it tries to guess where you're going to access memory next. And when you're following pointers, it's just lost. It doesn't have a chance. But when you're traversing a vector like this, everything is in contiguous memory. It sees that, okay, you access this memory location, and then a memory location, a fixed offset from that, and then another access, a fixed offset from that, and then another access, a fixed offset from that. And then it says, all right, I see what you're up to. I bet you're going to want to read this address too. So it starts loading it beforehand. And by the time you need the data, it's already there. So the prefetcher can really help with these linear accesses. So what we can do then is to change this to, where am I? Pull off and get record. Now to perf report. Perf report is not quite as impressive as K cache grind for visualizing, but the information is there. We can go into where do we have our load misses, and we can see that we have load misses in vector arrays, then move. We also spend some time here with in schedule timer with moving the data around. Okay, that makes sense. One thing that, by the way, with perf, as I mentioned, it does statistically check these counters from the CPU when it's running in this tight loop with many instructions. And of course, once in a while, we'll get things like this, where it claims that we have 9% of the cache misses in an instruction that doesn't access memory at all. But it's just because execution happened to be on that instruction when it gathered the pointers. So you have to be a little bit careful with how you interpret the results from perf, unfortunately. That is one of the advantages with call grind, that it gathers the statistics per individual instruction, but then it's super slow also. So I guess you have your choices. When I first prepared this presentation, I asked on Twitter what surprised you the most when you learned about CPU caches, and I got a lot of results, got a lot of answers, some insightful, many quite stupid, but such is Twitter. But I think Miro Knape, he just won. That doing more work can be faster than doing less, and I think this example showed this quite clearly, because all this data copying, it's so much more work, and it's almost 4 times faster. That is quite mind-boggling, actually, I think. So, do we have questions?
Not in the chat so far, but I actually have a question.
Okay, sure.
I never used tools like this, like Valgrind and Perf and so on. Do you have any beginner-friendly reading material or tutorials? Or any recommendations?
I will get to one thing in the end. There could be more. I can also mention that These are Linux-specific tools. I don't know if Valgrind is maybe available on others, but Perf is definitely Linux-specific. I know that Intel has a tool named vTune. I haven't used it personally. I have heard many people say that it's an amazing tool.
Yeah.
Unfortunately, also heard many say that it's amazingly expensive. So go figure. And I learned only today, actually, that AMD has a tool also called UProf. I guess it's like a micro profile or something like that. I know nothing about it other than that I've heard that it exists. Both UProf and vTune are available on Linux and Windows and BSD, I think. If you're developing on Mac, I'm sorry, I have absolutely no idea what tools are available.
That's okay. I'm a heavy Windows user, but Ninth Prime actually shared in the chat that vTune is free.
Oh, okay.
Yeah.
That is good. Yeah. So regardless, I haven't used it, but I've heard many say that it's an amazing tool, and I have no reason to disbelieve that. So it probably is an amazing tool.
Yeah, thanks. I will check that out.
Yep. Okay. So.
Sorry, there's one question in the chat.
Yep.
The question is, are you familiar with the top-down hierarchical analysis?
No, I have no idea what that is.
Oh, that was not a question for you. I'm so sorry.
Okay. Go ahead. Okay, so do I continue then?
Yes, I think you can continue.
Yeah. So, okay, so we saw in this analysis that even though it's a lot faster than the linked list, it's still expensive to do a linear search. So maybe we should do a binary search. It's worth trying. So we actually have exactly the same data structure. There's no difference in that at all. But what we can do is just to realize that this vector is now already sorted in timeout order. So we can use lower bound, which does a binary search for the insertion point, and then add our new element in there. This is linear for sure, but maybe we'll gain something. We'll see. And likewise with the cancel timer, I now change the timer value type so that it includes the deadline. So now when we want to cancel a timer, we can do a binary search with equal range to find all elements that has the same time, and then do a linear search in that small range to find the element to erase. And then the erasing that is, of course, a linear operation. So what happens when we try that? So binary search array. And try first just to get the comparable numbers here, and then we try the binary search. Oh, 0.39 seconds instead of 0.67 seconds. That is quite good. So we definitely gained a lot. 2 billion cycles instead of 4. Yeah, good. Instructions 1.3 instead of 7. Wow. L1 loads are down a lot. Load misses roughly the same, a little bit. Yeah, roughly the same. Lower, but not amazingly lower. But this one, what do you say about that? 101% of all 101% load misses. I cannot express how baffled I was when I first saw this. Like, how is it possible at all to have 101% cache misses? How? But it turns out this. You've heard about the Spectre vulnerability, and that is what we are actually seeing here. So what happens is that the CPU does, when it comes to a conditional branch, and the condition is not yet known what the value is. Should I go left or should I go right? It takes a chance. It uses previous knowledge from a branch predictor, and it takes a chance. I'm going right, and it starts executing the instruction for that one. And then when the condition result is available, it can see that, I was right, good, and then we get really good performance. Or it sees that, oh, bummer, I was wrong. So it throws away all the work, goes back to the branch instruction, and goes the right way. But here is the thing, that if that wrong path happened to include a memory access that was not in cache, the cache will select some entry, some cache line to evict, and will start doing a load. But that load will never land. It never comes to fruition because we never took that path, but we still evicted data from the cache. And that is what we see. That is why we see a load miss. And when we're doing binary search, we have the one tight loop where we go left and right, left or right, left or right, and there's nothing that the CPU can do to predict if it should go left or should go right, which is the right way to go, which makes more sense. It cannot do this. So regardless of whatever policy it has when it chooses which way to go, it's equally likely to be right and wrong. So we get a lot of these. And that, well, it's just the way things work, but keep this in mind. You can get a really weird result because of this speculative execution. We can do a record and see the details. Look at where we have misses. See, these are kind of hard to understand what they mean. I mean, these are mem move, sure, okay. So a lot of cache misses in mem move for sure. Shoot first. It's mem move and shoot first, of course. And let's see, where are we? And schedule timer. Can't really see anything. So it's difficult. Sometimes it's difficult to see much, unfortunately. That's just the way things are. 0.58%. I don't think we need to care much about that one. Sometimes it's difficult. That's just the way things are, unfortunately. Unless you're way more skilled than I am and know exactly how things are. But for me, things are sometimes. So what do we see that we can no longer see the searches at all. And this makes sense because since it is a binary search, we're doing very few accesses. It's 10,000 elements at most in there. And log 2 of 10,000 is what? It's not many, 13. So it doesn't matter. So of course, mem move dominates because it has to touch on average something like 2,500 elements in this. So what do we do then? We write a faster mem move, or this is a thing that always happens, or not always, but extremely often happens when you're trying to find a performance issue. Is that it turns out that mem_move is the culprit, and your task then is not to write a faster mem_move, but to make fewer mem_moves. So, and also, like I mentioned here, the failed branch predictions can lead to cache entry eviction, and it can be extremely confusing. So my thoughts here were, though, should we try a map? It's really popular to hate map, but it will do away with the mem_moves. So maybe it's worth it. Maybe it is. So the implementing is super simple. So it's a cheap experiment. Let's try. So we'd say that the timer is now a multi-map with a uint32 that is a timeout, and our timer data structure and is after comparison. And we use just the iterator for the timer information. So schedule timer is just an insert, and the erase timer is just cancel timer is just an erase. So it's a super dead simple implementation. And shoot first, just check if it's empty, return false. Otherwise, get the first one and erase it. So let's try this. So where were we with the previous one? 0.39 seconds. Map. On map. Oh. Wow. Wow. Okay, so maybe the map haters are wrong. Wow, interesting. Actually, this is too little information to have anything to work on. So let's change this loop. Instead of 10 times in the upper loop, let's do 1,000 times. Now, of course, we can't compare the numbers, so let's go directly to look at the recording. It takes longer because it does 100 times more work, but still not too bad. We'll look at the report. Where do we have our cache misses? Schedule timer, a lot of cache misses and schedule timer. Pretty new. And where are we? I'm not super familiar exactly with the implementation, but I know that the map is a red-black tree. It's a binary tree. So fortunately, we have some help with its pieces of source code in here. So we see that the misses are in comparing values, and we have this idea that this must be compare the desired timeout with the timeout for the tree node. Yeah, it makes sense that is expensive for sure, because these are again these are node based. We're chasing pointers. We get to random unknown places in memory where the prefetcher doesn't have a chance. So heaven knows. So obviously you get a lot of cache misses there. What else? Red-black tree, insert and rebalance. I don't think we have to go through more with that. Rebalance for erase on red-black tree. Now, what do we have here that takes time? This one is not obvious. This one is not quite obvious, but anyway, this is one of the lower things, 11% compared to the big ones. So can we draw any conclusions from this? Well, it's faster. Actually, it's a lot faster. But we see that comparing keys and rebalancing the tree is costly. And part of that is because it's node-based and we're chasing pointers, so we get cache misses wherever we land. But there's another thing also, and that is that the tree has a total order of all elements. And that is actually doing more work than we need to. We need to know which timer is the next to fire. We don't need to know which is the 18th. That is unimportant, but we get that information when it's a total order. And of course also the rebalancing to keep it in shape to be a red-black tree also is a cost in itself. If we look at execution time with the size of the data set, so the yellow one is the map. It's hard to see details, but we can see that for low number of elements, it's really slow. It's not until we get like 500, 1,000 or so elements that it's fast. So we can try to show this more, but by doing a normalization, so to compare with what the linear search in the array is. So linear search in array is one, fixed one. And we can see that the binary search is for few elements, it's slightly slower. For something like 100 elements, it's considerably slower, but then it gains. And the map is so much slower for few elements, up to 2 times slower. But then when we get to 1,000 to 10,000, then we get a performance boost. And here is also a thing to think about when we talk about cache friendliness is what size is your data set actually? These numbers, you may notice a total lack of error bars, so don't take these for the gospel in any way, but it's just to show the general shape. It's not untrue that it looks sort of like this, even though the exact numbers can be disputed for sure. But when you have small data sets, say 10, 20, 50 elements, linear search in an array is almost guaranteed to be the fastest. And when you have several thousand elements, then algorithmic complexity becomes something worth thinking of. And there in between is the difficult zone where it's hard to know. And you just have to measure and try. And so there is that. But one thing, though, that at least I thought of when doing this, can we get logarithmic lookup without chasing pointers? And we're getting to the heap. The heap is one of my absolute favorite data structures. Oh, by the way, are there questions? I heard that there were some sound effects. Okay, I'll get on then.
Sorry?
Yeah, were there questions?
Yeah, Andreas here. I had a question. I was wondering whether you could distinguish in the output whether your cache was destroyed by the branch prediction executing the wrong branch versus the prefetching things which you don't need. So does that lead to different outputs?
Not that I know of, but the prefetcher, you typically only get it wrong once, and that is when you get to the end of the loop. Then you have one access that was wasted. Whereas if you have like a binary search and you get it wrong and you get it right and get it wrong and get it right, it's a toss of a coin. But this is, I don't think, to my knowledge, but I'm prepared to be proven wrong. To my knowledge, this information is not visible. This is something you have to keep in mind when analyzing the result.
Yeah, thank you.
Were there other questions, or was that about that? Okay, I'll get on then. The heap. The heap is one of my absolute favorite data structures. It's kind of specialized, but it's really interesting for what it does. So A heap it's a partially sorted and perfectly balanced binary tree. And what I mean with partially sorted is that every node is sorted as the same or after its parent, but there is no relation at all between the siblings. So in this example, if you take the children of the root, the root is 3 and then its children are 5 and 8, we could switch place on 5 and 8 and it would be an equally valid heap that represents the same information. And then there is at most one node that has only one child, and that child then is the last node, and it's perfectly packed. There are no empty slots anywhere in this. So how this works is when we want to insert data into it, we create a space to do an insertion. But before actually writing it, we look at the parent, and we trickle down the parent if it is greater than the value we want to insert. And then when we have done that until there is no node to trickle down anymore, then we do the insertion in the space where it currently is. So in this case, if we want to insert 7, we make space for the insertion. We look at the parent and we see that it's 10. 10 is greater than 7, so we move the 10 down into a new slot. And now we look at this hole here and see that its parent is 8. 8 is greater than 7, so we move that one down. And then we look at the parent of this one is 3, but 3 is less than 7, so we move 7 up. And then to pop the top off, we just remove the top element and then we trickle up the lesser child. And then at the end, we treat the last element as if it was an insertion into that newly created hole. So we remove 3, trickle up the lesser child, which is 5, get a new hole, trickle up 6, which is a lesser child. Now we have 9, trickle it up, have a new hole. Then we have our 10, and we do as an insertion at that spot, which means that it could actually have needed to trickle up towards the root, but in this case, it wasn't necessary. And the cool thing with this structure is if we give each node a number starting from the root, and then just go down and to the right and increment the numbers. So one's children are 2 and 3, and two's children are 4 and 5, etc. We see an interesting pattern emerge that the index of a parent node is half that of the child, rounded down. And then also the left child of a node is the index doubled, which means that we can represent this tree as an array. And now we don't have to do pointer chasing. We can arithmetically figure out where to go because it's a doubling or halving. And that has a benefit because when you're doing pointer chasing, it's likely that the pointer itself is in cold memory. It's not in the cache. So you first have to wait for the pointer to be loaded from memory into cache so that you can read the pointer so that you can figure out where you should go. Here instead, you arithmetically know where to go. It may be a cache miss there, but at least you don't have to wait to know where to go to. But the problem is that the heap is not searchable. So how do I handle cancellation? Well, one thing you can do is a linear search, but then we're back to linear time again, so that is no fun. But what we can do is to instead split our data store into 2 parts. So we can have a store of actions where we just keep our callback and user pointer. And then we have our heap, which contains our deadline and an index into the action table, like so. And this means that we now only have 4 bytes that are working data that we move around in the heap up and down, whereas the actions stay still. And this is something you may have heard about from other places, like, for example, it's popular in games development to express data as a struct of vectors rather than a vector of structs. And this is the same idea, that you want to be able to touch only the relevant parts of your data to keep the working set small. So there are many ways to do this. This is one way to achieve this separation, to keep the working set small. The disadvantage with this is that the only reasonable way to cancel now is to set the callback to null, which means that the data structure will not shrink when we do a cancellation. If we look at this measurement program that I use to analyze the cache behavior, I cancel roughly half the timers, which is reasonably correct given the actual workload that it was used for. So this means that the data set will be on average twice as large as it needs to be. But this is log 2. This means that the tree is one level higher, and that basically doesn't matter at all in terms of data accesses. So how to implement this then? Well, it so happens that the heap is available in the standard library. It's hidden under the name priority queue. Priority queue is a container adapter, so you have to say that what your underlying container is. In this case, it's a vector. So the way you implement then schedule timer is to push the callback and the user pointer into the action store. I'm not showing the action store because it's not interesting, actually, I think. And then we push onto the heap the timer data that has the deadline and the action index, and then it will do this insertion trickle up thing. And then we return the action index as the thing to use when canceling. Shoot first now became a lot more difficult because the top element may be canceled, obviously. So we loop, look at the top. If it is has a null callback, we pop the top off and try the next one and the next one until we either get an empty vector or empty queue rather, or we get something that actually has a callback. And when we have a callback, we call it and return true. So this one became a little bit more involved. Let's have a look at what this can do then. So if we actually, I should start for the map for comparison. Then we build the heap. Okay, 1.17, 1.18, so almost twice as fast. 7 billion instructions, 2 billion loads. Yeah, fewer instructions, fewer loads. The map had 200,000 load misses. Half as many load misses, that is good. Branch misses 46. Okay, so we have fewer branch misses also, and that kind of makes sense because the tree, the map is a tree that keeps a total order of all the data, so it has to do more comparisons to ensure that everything is where it should be. All right. So should we maybe have a look at the details in here then? So do we have our load misses? Shoot first. Just heap, okay. Just heap, push heap. Can we see details in here? Okay, compare first child and second child and second child minus one. So it's to see which of the children to trickle up towards the root. And then we have these holes that we must fill, etc. So it makes sense that there is where we have the misses. Adjust heap. Same information. What we can see though is that there are no mem moves or anything such. We're past that, and we saw that it's quite fast. So a lot fewer, pretty much everything, and just about not quite twice as fast. So that is pretty impressive, I think. And if we look at the execution time, we see that it's a lot faster when we have many nodes. And this is my least favorite graph. I'm sorry, it's not a good one. But if we look at the heap relative to the map, we see that the map is always slower, or rather look at the map relative to the heap. The map it has the same algorithmic complexity. Both are logarithmic, but it's always slower. But still, comparing heap and a linear array, it's faster up until somewhere between 100 and 200 elements. Doing a linear array is faster, and for 10, 20 elements, it's a lot slower. So again, size of your data set is really important when thinking about where you should go. But there are still many cache misses in the adjust heap function. So I couldn't help wonder, can we actually do better? Now this is actually problem is solved. I'm just being a little bit obsessive here because I am like that. So if we look at the heap, how it looks, and how this is now actually stored in a linear array in RAM, and the caches are in lines of 8 elements, like so. And this is kind of unfortunate because we need to travel from the top to the bottom or from the bottom to the top. And we see that except for the top few elements, we get a new cache line for every generation we pass through the tree. And this means that we're not making use of the cache very well, actually. So even though we're not doing pointer chasing, we're getting to an address that is likely to be in cold memory, and then we leave it. We go to another place that is likely to be in cold cache, and then we leave it. So I wonder, can we do better? And what I thought about was try to represent it like this. So it's like we have a heap of small mini heaps where each mini heap fit in one cache line. That is neat. So can we actually do that? If we do, we see that we get 3 generations for every cache line, and that really should make a difference. So the way we can do this is to get our mini heap as an array, and then we toss in this 0th element that we actually just don't care about, not at all. The advantage with this is that since everything is now a size 8, it's a cheap bit mask operation. And then we have the next mini heap, and the next mini heap, and the next mini heap. We waste a little bit of memory, but we get fast operations and we get a lot of cache hits. And I should mention I actually tried an implementation where I did modulo 7 calculations on this, and it's dead slow. It has roughly the same amount of cache misses, but the modular arithmetic totally kills it. So it's not only about memory. And this, unfortunately, is really complex now. So I don't remember why I choose to call the mini heaps blocks in the code, but think mini heap when you read block. So we get an offset in a block from a generic indexing in the large array by just masking to keep the the lowest 3 bits. And then we can ask, are we at the, what is the block base for an index? So given a random element anywhere, where does that mini heap start? And then we can get then we can ask a question, is this a root? And so we can ask it, what's the offset within the block for this one? If it's 1, then we're at the root. And this is important when traveling up towards the root of the tree, because if we're at a mini heap root, it means we have to do the log 8 arithmetics to find the right place. And if we're not, then it's just halving the local index. So we get this thing to go to the left child of a node. We look at it. If it is a leaf, then if it's not a leaf, then we just double the local index. Otherwise, it's a horrendous maths, I'm afraid. And likewise, to go to the parent, if it's not the block root, then it's easy. Then we just divide the offset by half. Otherwise, it's horrendous arithmetics again. But for this to work, we need to make sure that our heap is properly aligned with the cache lines. So we use a line allocator that, to my knowledge, unfortunately, is not part of the standard library. But it's really simple to write one, at least if you're in C++ 17, because we have an align T type that we can use for aligned operator new and delete. So we just say, I need memory for n times this, and here's my alignment, in this case 64 bytes. So that is my requirement, and then it's up to the poor people who implement operator new and delete to fix that for us, but that's good. So let's have a look at this. Look at the B heap is actually the name of this structure. I honestly did not know that when I figured out how to try to do this, but it felt good to know that it has a name, because that means that several people have found this useful, so it's not a weird thing. So if we look at cache misses for the B heap, so we see 1.46 seconds, oh, it's slower. Oh, damn. But 82 million load misses compared to 102. Okay. Now there's one thing here. I'm using 01. Go to 03 and compare. So let's get the statistics. This one and the B heap. Now it's faster. Not much faster, but it is faster. But that is not actually important. What is really important is this: 85 million cache misses compared to 128 million cache misses. This is substantial, because if you think about this, I would actually use this one even if it was slower, at least if it was not substantially slower. Because if you think about it, this is a timer. This is not something that is executing in a hot loop forever and ever and ever. It's something that is called to schedule a timer, then the system does something, and then it schedules another timer, and then it does something, and then it cancels a timer, and it cancels another timer, and it does something, and it schedules a timer, and then it fires a timer. And by making sure that each of these operations evict fewer cache lines, it means that the rest of the system has more of its data in hot cache, which improves the total system performance considerably. And this is a detail that, in my opinion, is missed completely by most people who talk about cache efficiency, because everybody is so focused on this tight pipeline where you just want to do what is fastest, and the thing you do is the only thing that the system does, or at least that that CPU core does. But in this case, do a bit of work, do something else, do a little bit more work, do something else, and then keeping more of the entire system's data in hot cache really helps system performance. So yeah, about 2/3 as many cache misses as the normal heap. Not great speed difference. The shape of these curves are about the same. I think here the difference is small enough that I don't dare to say with confidence that it actually is faster on this level. I do know that it is faster in the actual use for the reasons I just mentioned, for the whole system performance. So time to round up, and I see that I have spent way much time here. What do I mean by being cache friendly? Well, for small data sets, linear search, linear operations in contiguous memory is the fastest, period. Algorithm complexity matters for large data sets. The crux is to figure out what is small and what is large. In my experience, but yours may differ, linear is typically king up until 100, maybe 200 elements. Above that, it's uncertain. And above 1,000, it's certainly faster to think about complexity. Avoid pointer chasing. Keep your working data set small. You may need to split data structure. You may need to use structs of vectors. And use a cache entry. If you have taken the cost of a cache miss, then don't just throw that away. Do something with it. Make sure that your data is represented in such a way that you can use more of it. And evicting fewer cache lines means more data available in cache for the rest of the program. This is obviously something that depends on the whole program structure, if this is relevant or not. Mispredicted branches can evict cache lines, and it can confuse the heck out of you. And measure. There's just no way, at least for me, no way to reason very much about this, but guided by measurements, you can reason about it. Some resources. Ulrich Drepper's paper, which is definitely not everything every programmer should know about memory, because he starts with how you make transistors from silicon. Millian Wolf had a presentation at a Qt conference a couple of years ago. It's an amazing talk if you want to learn how perf works. It's a little bit dated. There are a few things that are not correct, but mostly it is. Sorry for this absolutely horrible GitHub link to Travis Downs' cache counters rant. That was his amazing response to me being confused about having more than 100% cache misses, and it's great. Read it. And a little less than a year ago, Emery Berger had a presentation at a Strange Loop conference called Performance Matters, where he shows you how to do proper benchmarks and not to do the hand-wavy benchmarks that I did here in this presentation. It's an amazing presentation. So that was what do you mean by cache friendly, and here's how you can contact me. And extra bonus, here is where you can find the slides and the source samples. Thank you very much.
Thank you, Björn, for this amazing talk.